section or what? Class of items or objects. So by well-defined, we mean these objects must have something in common, either by a way of naming them or by the way they function. Example, we're going to give a number of examples. Example number 1, a set of numbers. We mean here, I mean counting numbers. The counting numbers, we denote this by say 0, 1, 2, 3, and so on. This is a set. Number 2, a set containing chairs, chair, table, desk. This is a set. It's a set of furnitures. So another example is a set containing pencil, protractor, ruler, dividers, and so on. It's a set of mathematical instruments, items in a math set. So that is why we call it a math set, meaning mathematics set of instruments, or set of mathematical instruments. Another example we can give is the set of countries. We can list some countries, and it's also a set. So like Ghana, Nigeria, Congo. This is a set of countries. We can also give another example, and in this example we say knife, spoon, and then maybe fork. So this is a set of countries. So there are many examples of such. We can give a set by listing some of its items, but sometimes we give a set by naming its property. We say X such that X will die. So what is X? Simply means X is a living thing, because all living things must eventually die. So this is all a set containing all living things. Kingdom Animalia are there, Kingdom Plantae are there, and so on. So we can also give another example as number 7 or 7th example. In the 7th example, we can say X such that X squared is equal to X. So this is also a set of numbers. Even though we have not yet introduced the set of natural numbers, that is why we are not being specific. It's a set of numbers whose square is equal to itself. We denote a set. By capital letters. For example, sets are denoted by capital letters A, B, C, D, and so on. So we say let A be a set. When you see a capital letter, we know we are referring to the set itself. So as sets, we write this as sets, while we write small letters A, B, C, X, Y, Z, and so on as what? We call them elements of the set. Elements of the set, or element of a set, or element of sets. So we write elements in a set as small letters, lower cases. Let's take a look at this example. items in a set are separated by commas. First item, comma, second item, comma, then the last item you close. And sets are enclosed, items in a set or elements of a set are enclosed in a curly bracket. See, open curly bracket, closed curly bracket. Look at how we have done it. So, we write A is an element of A to mean A is an element or belongs to. A is an element of A. If you see this means A is an element of A. An example here, we can write A is equal to, then we say A, E, I, O, U. So here, in this notation, you write A is an element of A, also E is an element of A, and then you can write I as an element of A, O is an element of A. Lastly, you say U is an element of A. Anything outside A is not an element of A in this notation. For example, call another letter out of A. Of course, here we are talking about the set of vowels in English alphabet. So, call another letter, say B. So, if we write B in relation to A, you say B is not an element of A. So, we cancel the membership. Say A does not belong to A. You cancel the membership because, of course, if you check the elements of A, B is not included. So, that is how we denote sets. So, if A is an element of A, we write this. And so B is not an element of A, we cancel the membership. So that is all about set notation, I think. Set builder notation. This is very important. We have started it as an example. Let's take example number 7. Set builder notation. We said X, so this is a set. Let's give it a name, X containing element X such that X squared is equal to X. So you need to pay attention and be careful here because most students are getting confused when we come to set notation, especially the set builder notation. So what we mean here, any number whose square is equal to itself, that is the number we are talking about. First, there should be a domain. Sorry about that. There should be a set where you have where you are concentrating. For example, what number, if you square it, gives it, it turns out to be itself. I can think of two numbers, 0 and 1, because 0 square is equal to 0, 1 square is equal to 1. To any other number, even minus 1 square is 1. So you see, not minus 1. So these are the two numbers. What we mean here is that this X is equal to the set of 0 and 1. Because these are the two numbers whose square is equal to themselves. If you square 0, you get back 0. Square 1, you get 1. So this is a set builder notation. You can also give another example, Y, such that small y, such that is a set containing y, such that y plus 3 is equal to 0. Well, this is actually a set. So how do we translate this? Sometimes you have given set notation, in builder notation, you need to solve the equation in order to get the number. Of course, you need to solve the equation. For example, so y plus 3 is equal to 0. You know y is equal to 1 minus 3. So this is a set containing minus 3. Let's talk about what is not a set. We have defined set, but what is not a set? Well, as we have defined set as a well-defined list, if the list is not well-defined, you are not being specific in the choice of those items, actually you will not have a set because there will be ambiguity. A member have a tendency of being in a set and have the tendency of not being in the set. For example, the set of all tall people. This is not a set because if you meet a very short person, a dwarf for example, very short, whoever you point at, no matter how short he is, to that shorter person, that person is tall. If you meet a taller person, if you show him that person again, you say, oh, this person is short. So you see, there is ambiguity. There is a tendency, if you meet somebody, you say, no, this is not a member of that set. This is a tall person. This is a short person. Another example, the set of fair people. Fair. Being white or black, complexion. You say, look at this. Somebody say, this is chocolate color. And somebody say, no, this is black. Somebody say, this person is fair. So these are not sets. So let's examples of types of sets. So we name sets based on either the number of items in the set or the type of items, the way the set is being constructed. Example, we have number 1, the null set. Or we call it the empty set. Empty set. This is a set without members. No member in that set. Then this is a set of, we call it a null set. Example, the set of human beings with tails. Actually, you don't see anybody with a tail, so the set of such people with tail is an empty set, actually. So, so 2, have the universal set. So this is a set that contains every item under discussion. The set that contains all elements under discussion or investigation. For example, if you begin to name the set of furnitures, if you say the set of furnitures, then any other furniture should be in that set. A universal set for furnitures. singleton set. Coming back to the empty set, we use this to denote an empty set, or we just write the curly bracket with nothing inside. That signifies the empty set. So singleton set. This is a set with only one member. Only one member. Contains only one item in that set. Just one member. Example, just write X. It's a set containing just one item. Just write the item and enclose it in the bracket. Even if it is not, even if it is a singleton set, you don't just write the item and leave it open like that. That is not a set. So you cannot equate it. Because this is a set, while this is not a set. So, fourth one, we have a finite set. Finite set. Well, a set to be finite, a set to be finite if you can exhaust the list of its items. If you can reach the end of the items, then that set is a finite set. For example, I have the set of numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take note that in this course, we may want to write 1 to 10, but to cut it short, we just write a set containing 1, 2, 3, and then we put 3 dots, and then write 10. Meaning, we are talking about a set containing 1, 2, 3, up to 10. Just as it is here, to make things shorter. So, this is a finite set because I have the last member. The last member is 10. Opposite to that is an infinite set. Infinite sets. Well, in this set, this is a set that you cannot exhaust the members. You cannot mention the last member of the set. For example, the set of natural numbers, this one. Let me formally define it. So this is a set of natural numbers. When we're writing things for the first time, we put this dot, and then equal to. We define it as a set containing 0, even though some mathematicians do not include 0, but we include 0 because counting starts from 0, from nothing, and then you have one item, like that. 1, 2, 3, 4, the counting numbers. You cannot reach the last member. So this is an infinite set because you cannot reach the end of the set by mentioning or by listing the members. Also, we denote the set Z, the set of all integers. The set of all integers denoted by Z is defined as. So we define it as the set containing many members, minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. It's also an infinite set. We are coming to other infinite sets when we come to number system. But for the meantime, these are the types of sets we have. I think we are going to stop at this time till we meet in the next video. Please do like our videos and subscribe. Thank you.